Right, welcome back. We are looking at pressure against volume curves now, and this is really a kind of key point that we've got to get our heads around, because almost all questions at A-level engineering involve some kind of pressure against volume curve when they're talking about thermodynamics. It's a very, very common type of question. So really none of this is new information if you've understood what we've done this morning. We've got a pressure and volume curve here. We need to be comfortable with those two axes and then kind of reading off what's happening on each of these lines. So we have different lines happening here. We can show different processes and you need to be able to identify them as we go. Now, we've got adiabatic expansion going here. And we know it's expansion because we're going from a smaller volume to a larger volume. And we know that because there is an arrow on this line. Whenever you are showing a process happening, you must have a line showing what's happening with the pressure and volume. And there must be an arrow in the middle of that line to make sure that we know which way it's going. Because obviously, if the arrow went the other way, this would be an adiabatic compression instead. Okay, so the arrow really does make a big, big difference here. So we've got two things that are happening here. These PV graphs are called indicator diagrams. Okay, so indicator diagrams, key phrase again, you've got to know what that indicator diagram means. And when we come to later in the topic, they'll talk about indicated power, and the indicated power comes from your indicator diagram. So again, just make sure you've got that kind of noted down. So we've got a compression. We're going from a higher pressure to a lower pressure at a smaller volume, and then we have an isothermal compression where we take it back to the same volume, but we do that slowly so that therefore we have an isothermal kind of difference there. We've got time for that heat to escape. Right, so we've got adiabatic expansion, great, and then compressed isothermally back to its original volume. Okay, two slightly different processes. Now, this is just naming this term here, V1, P1, P2, V2. So we are looking at, if we go from V1 to P1 to P2 to V2. What does that area represent? Well, we talked earlier about the line under the graph being work. Okay, so we've got work done by the expanding gas, and we know it's being done by the gas because it's expanding. All right, so work done by the expanding gas. We then conversely look at the next line, so V1 to P3 to P2 to V2 and back. That area, because we are compressing it, is going to be work done in compressing that gas. All right, so there's a difference in that amount of work. We have more work coming out or being done by the adiabatic expansion than we do to compress that gas back to its original state. So the question is, what does this area represent? So the difference in those two, what does that represent? Well, it's the net work done by the gas. Net meaning total or kind of summed up. So if you have like net profit, it's profit minus losses. All right, so net work done by the gas is the total work I took out minus the total work I put in to compress it back is the total amount of work that I've got done by the gas. All right, how could we restore the gas from P3, this pressure here, to its original pressure, pressure 1? I'm hoping that after this morning's lessons that you'll kind of know the answer to this. Now the question is, if I have a volume that's fixed, the only way that I'm going to be able to increase that pressure is to increase the temperature. Okay, so I'm going to heat up that gas while keeping it in a constant volume. Now, pressure against volume curves. Nice and simple. If the gas gets compressed, the work done on it, so the work done to the gas is the area beneath the curve. If it's reversed and it's allowed to expand, the work is the same area, but it's got the opposite sign. So obviously, going back to our first law of thermodynamics, expansion is a plus value of work and a negative value is a compression. Okay. If I go between those 2 points, all right, so if I compress it, up to that higher volume and then allow it to go back, okay, and it follows that same line, the net work done is 0. Okay, I have to put in the same amount of work that I get out when it expands initially. Now, this is the kind of graph that you can expect to see during an engineering question, okay, and this is an ideal gas pressure volume or an ideal gas indicator diagram. If the gas is compressed, the work done on it is the area beneath the curve. So where I'm compressing here, the area underneath that bottom line, okay, is the area I do, or the work that I have to do to compress it. The area below that top line is the work done by the gas. So you can see this grey area that I'm highlighting with the laser pointer is the net work that I get back from my gas. All right, and we're going to go into quite a bit of detail. If it's heated at a constant volume, no work's going to be done. Okay, let's look at this diagram. Where's it being heated? Well, if it's at a constant volume, I know it's going to be one of these vertical parts. And if we're heating the gas, the pressure is going to increase. So I've got this vertical line from 1 to 2. When it's allowed to expand again, it's coming down this line. And I have, as I said, that grey area is my network. All right, and then I have my gas cooled. So this is the kind of order of what happens. All right, so the gas gets compressed, it's then heated, which increases that pressure as a fixed volume. We've then got the work done by the gas as it expands, and then we cool it back down. We call this a closed loop. All right, because we've got a closed loop, we're taking an ideal gas, and remember we've got a non-flow process, so there's nowhere where these gases, etc., leave the process. So it's a closed loop. Now, this is really handy for us because we can use these diagrams to calculate the work done on or by a gas. All right, so as soon as we get this diagram, we can work out how much work is being done on the gas or by a gas, or we can work out the network. All right. Again, we know our ideal gas law, PV is nRT. So we've got pressure times volume over temperature is a constant. All right. We've got this NKT term, which again we'll come back to when you do your gas laws topic, the thermal energy topic. Don't worry about that too much at the moment. We can also use this to calculate temperature and changes in internal energy. So we're going to kind of use these ideas. Now, just going to run through an example question for you before I set you on your own kind of task. So we've got cylinder in figure 1. It's got a volume in here, 5,000 centimeters cubed. We've got a pressure that we're told, so 2.3 times 10 to the 5 pascals, and a temperature of 100 Kelvin. Your temperatures do need to be in kelvins. So if you're not confident in that, obviously 0 degrees is 270, 0 degrees Celsius is 273 degrees Kelvin. You need to be really confident in calculating those. Let's have a look. So the air is heated from 100 Kelvin to 275 at a constant pressure. Calculate the new volume V2. Right, so if we know we are at constant pressure, okay, we can knock pressure out of our equation. So we've got V1 over T1 is V2 over T2. Okay, we know the original volume, we know the original temperature. So V2, rearranging this formula, multiplying both sides by T2, is going to be the initial volume divided by the initial temperature multiplied by the second temperature. And it gives me a nice little volume here. And what we're working out is that we can use that to work out the second volume of what we're doing. Okay, so we can use these. It doesn't seem like there's a lot of information here, but actually we can work out quite a lot about these gases from the diagrams. What I want you to do is go away, do the questions on PV curves from the PowerPoint of thermodynamics questions and answers, and then you can move on to your next video.